Okay, so up to now, we've been looking at the SVM as a type of linear classifier. And if you recall back from the motivating example, we saw that linear classifiers are fundamentally limited, particularly for problems like image classification. So what I want to do and wrap up this unit is talk about the kernel trick, which is a very important technique for SVMs, which lets you easily extend these to certain types of non-linear classifiers. So to do this, we need to first start talking about what is a kernel function. So a kernel function is just a function k, which takes two values, xi and x, and typically they measure the similarity between some new sample and some training sample. So what we mean by that is that when the two samples are close, this kernel will typically take a maximum value, like this peak here or here. But when they're further away, that kernel is generally designed to go close to zero. And I'll show you why you want to do this. But before we do this, let's take a look at some common kernels. In the linear SVM, we'll show that it's related to something called a linear kernel, which is just the inner product of these two vectors. Now, to understand how that's a measure of similarity, remember from the linear inner product of two vectors is just the norm of the two vectors times the cosine of the angle between them. So this value will be high whenever xi becomes aligned with, in terms of angle, with x. That is, whenever the new training sample is aligned with the new sample is aligned with the training sample. But the most common for SVMs is something called the radial basis function, which looks like this. And if you look at this, it looks basically like kind of like a Gaussian bell curve with some peak at the training sample. And this 1 over gamma is the width. I'm going to go through this in a little more, but let me just walk through one final example, which is sometimes called the polynomial kernel, which is just the inner product as before, but raised to some power d, and typically that power is 2. This is the RBF is the most common, so let me walk through this a little bit more, give a few more examples. So the RBF is this exponential, and you see that it has this parameter gamma. And if we look at this, as if we fix x0 and plot it as a function of x, this will have a peak value of 1 when x is equal to x0. And it'll decay kind of at a rate of 1 over gamma. First, let's look at what that looks like in 1D. In a 1D example, I've plotted two RBFs for different values of x0. When x0 is 0, it takes that peak at 0. When x0 is 2, it takes a peak at 2. And the gamma value tells you kind of the width of this. So higher gamma values mean a smaller width. You can also do this in 2D. So in this case, I've plotted 3 different examples with 3 different centers. Again, in each case, it takes a peak value of 1. And as gamma increases, you see the width of that kernel decreases. All right, now that we've understood what kernels are, we want to go to something called the kernel classifier, which will help you understand the SVM with classifier. So a kernel classifier is very, very easy. All you do is, suppose I have some training data, and let's say they have binary labels plus or minus 1, and I pick some kernel. The kernel classifier then says, okay, if I have a new point, I do 2 things. The first thing is I compute something called the decision function, which is this, and then I take the sign of that decision function, and that will give me my best estimate of what is the class of this new point. Now, to understand this function, let's look at this decision function. We see this. Remember that the kernel is selected so that it'll be high whenever x is close to xi. So this sum here will be a large positive value whenever x is close to yi's, which are positive. And similarly, z will be negative whenever the test sample is close to training samples where yi is negative. So it basically takes the x, it looks at training samples close to the x, and based on the sign of those training samples, it makes the decision on this test sample. Now, kernel classifiers are a whole subject of their own, and we could have actually spent an entire unit on them. But I just want to mention them very quickly here to talk about the connection with SVMs. So that was equations. Let me show you it more graphically, and it'll make it more clear. So let's look at a very simple 1D case. So let's imagine I have 6 data points. I just made these up. And each of them xi is a scalar. And again, we have binary labels, plus or minus 1. And I fit a kernel classifier with our radial basis function kernel. So the first part is that we take this decision function, which is of this form. Now what is this? This will be a sum of these kernels, but each of these kernels is a bell curve with a peak at xi. So that's what these dotted lines are here. So the green dots are the training samples, the yi's for the training samples, and for each one you get a bell curve with a peak at that training value. Then when I sum them, what will happen is the z will be negative whenever you're in the vicinity of negative training samples, and it'll tend to be positive, like here on the right, when you're ever in the vicinity of positive training samples. So then when you take the sign to make the classification decision, that is this green line here, you can see what actually ends up happening. So for any x where you're close to training samples which are positive, it guesses it's positive. And similarly, when you're close to training samples which are negative, it guesses that it is negative. Now, one important thing about this is to look at the effect of gamma. So I've done the exact same plot as before, but I've plotted for 3 different values of gamma, both the decision function in blue and the classification rule in green. And what you can see is that as gamma increases, the z becomes close to yi whenever x is close to xi. So for example here, it's actually almost exactly fitting this training data. And in general, as you increase gamma, it will tend to fit the training data better, and you'll be able to get a more complicated decision region. So as a classifier, if we did kernel classification, increasing gamma would result in a lower bias error because it can fit the training data, but a higher variance error. I'm not going to be talking much about kernel classifiers, so this is not super relevant at this point, but I just want to make that point clear because a similar property will happen with SVMs. All right, now that we understand kernel classifiers, we can look at what happens with their relation with SVMs. And their relation happens whenever we use SVMs with nonlinear transformations. So what do we mean by a nonlinear transformation? If you recall from even right back to the very first lecture on multiple variable linear regression, whenever you're doing a linear regression or a classification problem, you can always replace the x with some nonlinear transformation. And that will allow you to get more rich nonlinear classifications or regression rules. So for example, if we took a scalar x and we mapped it to the powers of x, the d powers of x, and then we did a linear combination of these terms, we'd basically be able to get a polynomial classification rule. Now, the way that SVM people think about this is that you're performing the classification in a feature space. So for example, let's say I have some input space where the data looks like this. And it's clearly not linearly separable because a good boundary would have some complicated relationship. So what you can do is take this phi and map it to a higher dimensional space, or typically higher dimensional space. And in that space, there is some linear separability. And then when you map back, you get this non-linear, more interesting boundary. Now, you can do this with any classifier, or this is a very common method, and we've already done this. What's important about SVMs is that when you apply this linear transformation, you can do this very easily in a kind of kernel domain, which I'll explain momentarily. All right, let's look at what happens when you use the nonlinear transformation with an SVM. So that means I take the SVM model and do everything I've done up to now, excepting I replace x with phi of x. In particular, I go ahead and minimize the SVM cost function, which is that hinge loss plus inverse function. The key result is the following, that when you do this, the weights will have this form. They'll basically be a linear combination of these phi of xi's, where xi's are over the training samples. And moreover, the alpha i's in this will be positive, and they'll be greater than 0 if and only if the training sample I is a support vector. Now, I'm going to not show this in the video, but in the next set of lecture notes, you can go through the proof of this, and it's just some results in constrained optimization. But we just use the fact for here. So when you do this, if you look at this W, and I substitute the W into our linear discriminant from the SVM. So the linear discriminant is B plus W transpose phi of x. I add a new sample, and I substitute it in, I get this expression here. But if you look here very carefully at that last term, we have this inner product of the transformation of the training sample with the transformation of the test sample. And this is what we're going to call in the kernel for the SVM. Now, why do we care about this kernel form? Let's look at the final kernel, the classifier that we get with the kernel, with the SVM. We see it as two parts. The first part is this decision function, and we see the kernel showing up like this. This is just the exact expression I took from the previous slide. And just as before, for the classification rule, I take the sign of that decision function. And what we can see from this is that it looks approximately like the kernel classifier that we've been talking about up to now. There's just two differences. The first difference is that there's the introduction of these terms alpha I. So it's like a weighted kernel classifier where it weights certain samples, training samples. In particular, it only weights the samples with a non-zero value on the samples that are support vectors. The second is this first term here, which is this bias term. And that bias term will let it select when, make the sign of this, whenever all these values here are small. Let me mention something called the kernel trick. So this is the kernel form of the classifier from before, the previous slide. And what we see here is that the classifier, you can say, is parameterized by these values alpha. These values are typically called the dual parameters because of their relation to optimization, which again, you can look in the notes to get more details. The kernel trick says that instead of actually optimizing over the weights, we directly optimize over the alphas. And that optimization itself just uses the kernel. I'm not again going to show this, but the point is that you don't even explicitly ever need to look at the phi of x's that generated this kernel. All right, now let's take a look at what the SVMs will typically look like. So here, again, is our 6 simple data points as before. And I fit the SVM with different values of gamma. When you do this, you kind of get similar trends to what happens. The decision function here will tend to look positive when it's in the vicinity of positive samples and negative in the vicinity of negative samples. Also, as I increase gamma, that function begins up fitting the data better and better, like this. All right, and that will let it fit more and more non-linear regions. We can also do this in 2D. So in this case, I've taken, I think, 10 data points, and I've plotted on the left here the decision region. So remember, in 2D, what happens is that each kernel is kind of a two-dimensional bell curve. And again, it will be positive close to the positive samples and negative close to the negative samples. So when I take the sign, I get this region which kind of interpolates that training data. And again, as I increase gamma, I can get more and more complicated decision regions. Now, that fact leads you to realize that SVMs actually have with the kernel method, have two parameters that you have to select. As before, you have to select the parameter C, which weights the hinge loss versus the margin. But you also have to weight this kernel width or whatever other parameters are in the kernel. Now for both of them, what happens is that as you pick either higher C or higher gamma, you tend to have fewer number of support vectors. So the classifier is averaging over a smaller set. And that will result in a lower lower bias, but a higher variance. And just as we always do when we have a bias variance trade-off, we can select that C gamma pair through some kind of cross-validation to find which is the highest accuracy on the test data set. So this plot on the right does exactly this cross-validation for the MNIST data that we saw earlier. So in this case, we're looking over both values of C and values of gamma, and these contour plots show the lines of the test error for different C's and gamma. And then what you can do is you can pick the C and gamma, which gives you the highest or lowest test error or highest test accuracy. Now, you can go to this site, which did all of this. This is extremely, extremely slow because each point we'll see takes a lot of time to actually compute, but I'm just going to use these parameters that this person found. Python also has a way to automatically do this grid search, and if you do the lab in the bonus section, you can walk through that. Okay, one last thing that we need to talk about for SVMs is what happens when there's multiple classes. Up to now, I've done everything with binary classes. When you have K classes, you have kind of two approaches. The first approach is you train one SVM for every pair of classes. And then in the test phase, you kind of assign the sample to the class that wins the majority of votes. So that gives you typically the best results, but it tends to be very slow. The other option is what's called a one versus rest. And in that case, you train K SVMs, one for each class against all the other K-1 classes. And then you pick the class which gives the highest score. In sklearn, you can do both, but we'll just use this one for the MNIST case, the one versus one. All right, let's look at what happens in the SVM. At least in terms of coding, it's very easy to do. All you do is you create your SVM object, and then you give it the kernel, which is radius and basis function, and you give it the parameters. So if you use SVM, you have to find your own, on a different problem, you have to find your own parameters. But these ones I just took from what that other person found, because it's very slow searching over these C and gammas. Then you fit on the training data, and this is super, super slow. This will take a long time, so I'm not going to bore you with waiting for that. But after it's done and you run the prediction, in this case, you get about 98.4% accuracy. And that's much better than what we were getting with the simple linear models. It's not state-of-the-art by any means, but without too much work, we can get a pretty accurate classifier. Let's just look at some of the decisions it made, or actually let's look at some of the errors. It still makes errors. So for example, in this case, the true digit was 7, but the classifier estimated that it was 9, and this was true was 8, the classifier was 5, and so on. So in this case, maybe a human would have guessed some of these, but you can see that all these digits where there are errors are really badly written digits. So a human would have guessed, for example, that this was a 7. But you can see why the MNIST classifier, the SVM classifier, got confused and thought it was a 9. This digit here was just a really badly written digit. I think I would have guessed that it's a 6, but it's actually an 8. And this one's actually also very unclear. And this one, I guess I would have guessed it's a 9, but you can see it's a very badly written 9. So it's actually hard for the classifier to do a good job on this one. So it still makes errors, but unlike the linear classifier, it's making errors on actually only the more complicated digits. All right, so that wraps up what I want to talk about for the kernel method, and this should give you everything you need to do for the problems, for the labs, and any other types of SVM problems that you might want to use.